So I want to talk about a problem. It's called the Atwood's machine. And this is a subject of the interacting objects topic. And it's going to be using ropes and pulleys. And we're going to use the ideal approximation of ropes and pulleys. This occurs when the rope and pulley are massless and frictionless. And this is an approximation in real-world cases, but that's what we're going to go with, and in many cases, it's a good approximation. In a later chapter, we will learn how to deal with cases where they're not massless or frictionless. So this is Atwood's machine. We've got a pulley here, and we've got a rope here, and that rope goes over the top of the pulley. And then we have two masses. So we're going to have a smaller mass that we're going to call little m, and we're going to have a bigger mass that we call big M. And as you might imagine, if there's a heavy mass on one side and the light mass on the other side, this is all going to go this way. And just to prove it, I made a video. This is my amazing cinematography here. Let's scroll back to the beginning. On the right-hand side, you'll see a mass, and the one on the other side you'll see as it flies by. And so we get an accelerating system, and the acceleration depends on the masses that you have, and it depends on g. And that was, in fact, the purpose of Atwood's machine, was to slow down the effect of gravity so it could be measured more precisely. So we are going to find the magnitude of the acceleration. And I'm saying magnitude because they're moving in different directions, right? The blue one has an acceleration pointing down, and the red one has an acceleration pointing up. So they're not going to have the same direction, at least in space, but they do have the same magnitude. And in fact, that's one of our constraints. But let's look at the forces on them first. So I'm going to draw a free body diagram. I sure am. Here they are. And we will call this one the free body diagram for little m, and then we will do a free body diagram for big M. Here we go, big M. Okay, so on little m, what are our forces? Well, we have a downward force of gravity, and I meant to write that as, that's fine. This is the force of gravity on the little one, and this little m is the same as that little m. That's the mass of the actual thing we're talking about. And we have a tension pointing upward. And we know that the tension upward is going to have to be larger than the weight because the mass little m is accelerating upward. So I'm going to call this T1, and we will talk about why I did that in a little bit. Over here, we've got our forces. Let's go ahead and draw the tension first, because we know when we have an ideal rope and pulley, where the rope and pulley are massless and frictionless, the tension is the same everywhere. Tension has same magnitude everywhere. So if the little mass is pulling on the string with a tension of 10 newtons, then that 10 newtons will also be pulling up on the big mass. This is essentially Newton's third law, just being like transformed around through this rope. So we have a tension that is also going to be 4 tick marks long, or sorry, 5. I can count, I promise. I am going to call it T2 because these two tensions act on different objects, so technically they're different forces, but it's okay. We know what we're talking about here. Well, what direction is the acceleration for mass big M? We know that it is moving downward, and so its net force needs to be pointing downward, and so I'm going to make its weight 6 marks. And that way we have more weight pulling down on big M than we have tension pulling it up. We have more tension pulling up on little m than we have weight pulling it down. I am going to complete tau charts for these two, and the reason for that is to make sure that we know what our constraints are, what forces are equal. So we have tension by the rope on mass little m, and we have weight by the earth on mass little m, and the same things over here, right? We have tension by rope on mass big M, and weight by earth on mass big M. And our observation is that we have the same rope for those two, so those two tensions must be the same. So we're going to, next stop is going to be our constraints, and then our force pairs. So constraints are on the acceleration. Now, there are different ways to do this. I'm going to do the one that is probably the most straightforward to think about, which is to put our coordinate system where y is pointing vertically like that. And so the acceleration of little m is going to be a positive number, and we'll just call that positive number a. And the acceleration of big M is going to be a negative number, but it's the same magnitude as the acceleration of little m, right? Because for every centimeter that big M moves downward, little m has to move up 1 centimeter. And so if big M is moving down at a centimeter per second, little m has to be moving up at a centimeter per second. So the accelerations, and in fact all the kinematics, are linked between the two. So we can basically repeat those two equations down here. The acceleration of the little mass is equal to a, and the acceleration of the big mass is equal to negative a. Force pairs, we've basically got this already. The magnitude of T1 is equal to the magnitude of T2. Now we're going to write Newton's second law for both objects. So for little m, we have the sum of the forces in the y direction. It's equal to little m times acceleration of little m. Well, what are the forces? We've got tension minus the weight, and that is equal to the mass. And we're just calling an acceleration little a. Did I get the colors backwards already? No, colors are good. For big M, we've got sum of the forces in the y direction. It's equal to big M, acceleration of big M. What are the forces? Well, we have tension up, we have weight down, and that is equal to mass times the acceleration of big M, which is just negative a. The last thing I'm going to do is observe that since our tensions are the same, we might as well just call those T. So I'm going to rewrite these two equations with plain old T in them. Okay. And now, if we look at our equations, we've got two equations and two unknowns. We don't know A, we don't know T, we don't know T, we don't know A. So we want to solve these two equations in order to get the unknowns. The only unknown that I specifically asked for was the acceleration. So we can eliminate the tension from one of these equations and get the acceleration. The way I like to do this is to subtract the two equations. So I'm going to write two equations underneath one another. And then I'm going to subtract this whole equation. So that means I'm going to change the sign on each term, and then I'm just going to add these two together. So you can see that the tensions cancel out, and I've got big mg minus little mg, and then I've got little ma plus big ma. I'm trying to solve for a, and so we've got big M minus little m times g is equal to little m plus big M times a. Boom, we've got it. And let's just make up some numbers here, just to put some in. We'll say that little m, actually we can go with the numbers that were in the video. It actually doesn't matter if you convert these to kilograms for finding the acceleration, because the units are going to cancel out. That's fine. So we have A is equal to m minus little m, so that's 20 grams. This g is not the same as this g, right? These are units g. And this one is 420 grams. And that's, I don't know, it's something. 10 over 210. You know calculators, you can do it. I'm going to stop there. Obviously, we can now solve for the tension if you go back to one of the previous equations and plug in our acceleration.